Can everyone hear me? Sounds like yes. Okay. So I'm Christopher. Like he said, I'm from Shopify. We're a Canadian e-commerce company, but we have people all over that work remotely. So a couple things before we get started, and I address the ridiculous title. So first of all, just in case at any point in the talk I say the word I want you to hear we. I didn't do any of this alone. So there was a whole team, and then like people even outside the team that helped. So this was a group effort. But anyway, so this title has a lot of words in it. You may have noticed. And the biggest problem is that it brings in two different kinds of people. There are people who have heard some of these words before and would like to kind of get a sense of how these tools work and what they are in a context they understand, in this case Kafka. But it also, the other sorts of people are people who maybe have done this before and would like to see if we encountered some of the same problems or if we solved them in similar ways. Or they got stuck at some point and wanted to know how we got past it. So unfortunately 40 minutes is actually really short, and I can't do both, so the talk is predominantly going to be for that second group of people. I'm going to have about 10 minutes where I introduce the concepts of Kubernetes, mostly defining terms and refreshing people if they already know it, and if they know similar systems, then they might kind of pick up on the specifics. But mostly I'm going to get into the meat of it because you can go read a Kubernetes tutorial online. And for online people, I recommend you go read about StatefulSets now and then come back. The next 10 minutes will be a bit of a refresher on that. But okay. So the first thing is definitions. So Kubernetes, you may have heard of if you're here, and you may even not have. So Kubernetes is an abstract scheduler and orchestrator. That's basically its job. There are others like it. Apache Mesos is similar, I'm led to believe, though I haven't actually used that one. But basically it solves the problem of, by the way, my timer hasn't started, in case that's a problem. Okay, so it solves the problem of I have all these machines, and I would like to, and I have all this work that I want to do, but I don't want to actually pick which machines do which work. I don't want to have web servers 1, 2, 3, and Kafka brokers 4, 5, 6, or whatever. I just have many machines, and I want to treat them all kind of fungibly. And then I want you to have the machine go put all the work on all the machines. That's basically its job. Some of the machines might have different constraints. Some of them might have more RAM than others. Some of them might have more CPU. Some of them might have like a GPU or something. But basically, I want you to take the work and then fit it everywhere that you can. So this little part here is just basically going to be a quick introduction because I don't have time to go into it further. But hopefully, it'll be okay for everybody. Yeah. Okay, so the very first thing, and like I said, mostly this is going to be definitions. So the very first thing is nodes. Kubernetes calls the machines that you run things on nodes. These are the things that things get scheduled onto, nodes. This is important. I'm going to say this word a lot. We're not talking about Kafka brokers. Nodes are the machines that things run on, unless I screw it up, in which case I might be talking about Kafka brokers. So these could be physical hardware in a data center or something that you're running machines on if you're running this. But it also could be VMs if you're running in the cloud or something. It could be some hybrid system. Basically, these are things to be scheduled onto. And like I said before, they can have different capabilities and configurations from each other. But we'll deal that later. The things that you want to run are called pods, which I've done by these pinkish circles. Actually, the contrast is not too bad on the slides. That's good. So basically, these pods are the actual things that you want to run. They can have different requirements. They can have different amounts of RAM that they need. They can have different amounts of CPU. And then, again, it's Kubernetes' job to fit them where there's still space onto the nodes. Pods scheduled onto nodes. Okay. Containers exist inside a pod. A pod is built of containers. Basically, the reason for this is that Kubernetes schedules pods. It schedules all containers from a pod together because it doesn't schedule containers, it schedules pods. This can be useful, so for example, if you've got a Kafka broker and you've got a thing that reads the JMX and reports metrics or something, they will always be together. Whichever machine they end up on, they'll be together. And they also do things like they share a network space, so the metrics container can always refer to the Kafka broker as localhost. And even if there's 6 Kafka brokers on a machine, the one that I am associated with is always localhost 9092, for example. And they can also share directories and stuff. You can poke holes through the isolation that containers provide, so long as they're within a pod, which can be super handy in a practical sense. And like I said, they always end up on one node together. Yeah, okay. So if you've got all these things that run all over the damn place, and they get scheduled onto nodes, and you don't know which nodes they end up on, because that's the computer's job, you have to be able to talk to them somehow. The Kubernetes abstraction for this is services. So I've got this elongated teal box with some arrows. I'm actually pretty proud of this. So basically, this is an abstraction. It has an IP and a DNS name within the cluster. And the pods are labeled just with like tags, like app equals Kafka or whatever. And a service has a selector, and basically it will find all of the pods wherever they're scheduled that match that selector, and it will randomly load balance to them. So anyone who talks to the service will receive a pod that is ready wherever it is in the cluster. So this is kind of how Kubernetes allows things to access each other as a kind of simple service discovery. There are other service discoveries that you can run in Kubernetes. I haven't touched any of those, but they are even a level above. And then also importantly, if like this guy in the middle here were to suddenly, if that whole node were to go away and that workload were to get rescheduled onto a different one, work would not get sent there while it's down, and then when it spins up, work would start getting sent there again. Okay. Okay. So the other thing is there's a whole bunch of Kubernetes resources for doing stateless things, like, give me 15 web services. I don't care what they are, just give me 15 of them. That works great, but I don't have time to talk about them. So instead, I have to talk about StatefulSets, which are the more recent Kubernetes resource for doing things that are stateful, like Kafka. Because Kafka doesn't work as well when you have brokers that are randomly named and then disappear and never come back. So what StatefulSets give you, they give you a couple features that normal Kubernetes things don't have. Oh, by the way, StatefulSets used to be called pet sets in earlier versions, if you're ever looking at a blog post. But now they're StatefulSets. So basically, the first thing they give you is they give you stable names. So Kafka 0, Kafka 1, Kafka 2, rather than Kafka random suffix. And it also has the advantage that it gives you a consistent set of names. So if I ask for 10 replicas of my Kafka brokers, I get 0 through 9 every time. And if Kafka 4 dies, the thing that replaces it is also Kafka 4. You don't have a thing that just goes away and, like I said, never comes back, which is bad for these kinds of operations. Oh, by the way, the stateful set is this diamond here with the little dots, and then there's numbers. Okay. The other thing it gives you is a network identity. So the Kafka brokers can talk to each other, and things within the Kubernetes cluster can talk to each other using a DNS name that specifically identifies a single broker. You don't have to go through the service that randomly load balances out to everything, which, again, not good for Kafka because you have to be able to individually address a particular broker. So this will give you kafka1.kafka.kafkaproduction.service.cluster.local or whatever. And no matter which machine Kafka ends up on, Kafka 1 will always be there, and you can route to it specifically. And the last thing that it gives you is persistent storage, which I've used the normal persistent storage icons for. So basically, you can have a template in your stateful set where you say, I would like every broker to have 4 terabytes of storage or whatever. And the stateful set will take care of making sure that always is on the box that you are scheduled onto. So when it spins up Kafka 1 on this machine here, it'll say, okay, do I have a Kafka 1 data directory? If so, I will attach it to the node, and then I will mount it in the container. And then when I start up, I will have Kafka 1's data. And then if that gets scheduled to another machine, it will detach it from that node, it will reattach it to this one, mount it into the container, and then I'll have Kafka 1's data again. So every time Kafka 1 dies and comes back, it'll have the same name, it'll have the same data, and there will only be one of it. So basically, pretending that there are machines in a system that's not about machines. But those 3 things are important because stateful workloads kind of need those, or our kind. With all of those things, you can go find a tutorial that does similar things, right? It'll take you 15, 20 minutes or whatever to go spin up a Kafka broker and some zookeepers and you'll get into, you'll have something that runs. It'll be pretty great. The StatefulSets handle things like rolling restarts, all that kind of stuff. It's all in there. So the problem, though, is that things are not all perfect. And some of these are my fault, and some of them are Kubernetes, and some of them are just a difference. So basically, the first thing here is you might turn this on at some point if you are just kind of cobbling together scripts from places you found on the internet, and you maybe you're spinning up your zookeepers, and it'll turn on, and then it will die immediately. And then Kubernetes will notice that it has died, and it will turn it back on, and it will die. And you'll end up in this crash loop, and then Kubernetes will start backing off, like with an exponential back off, so that it's not constantly dying. And you'll say, that's weird. And then you look into why did it die, and you'll find out that it ran out of memory, which is also weird, because it didn't do anything yet. It just kind of started. So that's kind of strange, but eventually what you might discover is the heap. So the JVM has a heuristic when it starts up for figuring out how big of a heap to allocate if you don't give it an explicit one. And Kubernetes has a system where you can say, only give this pod 20 megabytes, or okay, let's say 200 megabytes of RAM. The problem is that Kubernetes limits are based on Docker limits, which are based on cgroup limits, and those things don't actually change the machine. We don't have a virtual machine here where you only now have a machine with 200 megabytes of RAM. It just provides a limit, and at which point the kernel will cut you off and kill you because you're out of memory. This can be bad because the JVM, up until very recent versions of the JVM didn't know about these cgroup limits. So it would start up on a machine with 110 gigabytes of RAM. It would say, oh man, I have all this space. And it would allocate a huge heap and immediately die, even though it hadn't done anything. So this one is not too bad, but it can be a little bit confusing and a little bit disheartening when you finally start this thing up and all it does is just die because it's out of memory all the time. This one, though, has a pretty easy solution. You just give it an explicit heap. You should probably do that anyway, but maybe you were cutting corners because you were lazy when you were doing an experiment. And yeah, so it can be a little bit confusing. All you have to do is give it an explicit heap and make sure that that heap that you give it is lower than the memory limit you specify, or else it'll keep getting killed. Again, probably right on startup. So this is great. So at this point, your machine is running, and you've had the cluster running for a week. It was actually pretty easy, and everything's talking to each other, and everything is fine. And then at some point, you decide I should probably test this resiliency thing that I was hoping this would give me, and you kill Kafka 7. Kafka 7 goes away. Kafka 7 comes back. Everything's lovely. And it catches up on the things that it was behind on, and then it becomes an in-sync replica for some of the topics that it is assigned to. And then everything starts going bad. And all of a sudden, Kafka 5 and Kafka 9 are now out of sync on all of those topics. And you look in the logs, and you find out that it can't see Kafka 7. It's been trying to contact Kafka 7. It can't see Kafka 7, so it can't replicate from Kafka 7. And so everything is out of sync, and it's bad. And you think, that's strange, because it was working for like a full week. And then you're like, okay, maybe something's wrong with Kafka 5. So you kill Kafka 5. Kafka 5 comes back. Kafka 5 can now talk to Kafka 7. Kafka 7 can't talk to Kafka 5 anymore. And Kafka 3 can't talk to Kafka 5 either. And you're super confused about this. And at some point you do a whole rolling restart. You like turn everything, like let's just do a rolling restart now. Nothing can talk to anything. And and you scale down to 0 because, oh right, so StatefulSets make it really easy to just say replicas 0, enter, and then they all turn off. That works. I mean, it works. They all go away. And then you scale it back up to whatever you had before, and then they all come back. And they can all talk to each other again. And it works for another week, and then maybe a node goes away while you're sleeping in the middle of the night, and now things are out of sync again. The whole story starts over. So it turns out that JVM is very aggressive when it does DNS caching, as in, like, by default, always cache forever, positive and negative lookups. Which I was surprised by. And the problem is that this works great when you have a machine that is Kafka 7, and this machine is the machine, unless it like explodes in fire or something. But in Kubernetes, every time a pod goes away and comes back, it comes back with another IP. And the DNS changes, those stable network names I talked about. Kafka 7 is still routable, but the IP has changed, which means even if you, the equivalent of SSH into the Kafka 7 broker, and you use the Kafka tool and you go talk to Kafka 7 from Kafka 5, it totally works. Even though Kafka 5 is saying, I cannot talk to Kafka 7. Super confusing. Turn off the cache, or reduce it, but probably just turn it off. I mean, they don't look at each other up very often, right? These things aren't dying all the time. And then at that point, like I was saying, you were getting to this weird split brain where things could only talk to things that were older than it. Because if at any point I'd looked up Kafka 7, and then Kafka 7 went away and came back, all of the existing brokers were now looking at the wrong address. But the newer things could talk to all the old things, because it's a weird caching issue. So it's super hard to debug, or it was for me. Maybe you guys are great at this. So it can have weird side effects, and you should just turn off DNS caching. So you do that, and now your Kafka broker is great. You can roll the Kafka brokers. They're resilient. Everything is lovely. But Zookeeper is not. Even though you've turned off DNS caching on Zookeeper, you have the same kind of weird problems, which are even harder to debug because the logs are a little bit less obvious. You know, the Kafka logs are more like, I am the leader of this, and I can't talk. I am Kafka 5. I cannot talk to Kafka 7 about this topic. Whereas Zookeeper is just like, I don't know. I'm not serving requests right now. So you have the same problem. You've turned off DNS caching, and you still have this problem. So it turns out that Zookeeper has one bigger issue where the Zookeeper actually stores in its business logic, it has a connection object, a Java connection object, and it stores the domain, like the DNS resolved IP, in there. Like it's just in the list. So every time it sees a new host, it goes and it does a lookup, and then it stores the IP and then never looks again, because it was like, oh, this connection's already in my list. I don't have to do DNS, because it's super expensive, apparently. So anyway, I never found a way to turn it off besides like patching Zookeeper, which I'm not going to do. So that is like I said, it's even harder to detect. And again, you have this rolling split brain where like half the cluster can see each other, but never in a bidirectional way. It's super crazy. So the problem is basically I've got this, right? I've got my 3 Zookeeper pods here, and they're all talking to each other. Obviously, they can also, yeah, anyway. So they're all talking to each other, and if this pod up here on the top left dies, then the existing pods can't talk to it anymore. Super weird. So basically, the only way I could come up with to solve this, and maybe it's a bad one, is to reintroduce services, because services have static IPs. Or I can give them static IPs. So in this case, if you remember my services here, they load balance, but these services do not. Well, I mean, they would, but there's only one thing. So if I label each pod uniquely, like Zookeeper 0, Zookeeper 1, Zookeeper 2, and I have a service for each of these things, then each service would load balance, but there's only one entry, so it just kind of like goes to the one that I wanted it to. So I've got a Zookeeper 1 pod and a Zookeeper 1 service. And this is great because, like I said, I can construct these services with static IPs, and more importantly, during normal operation, when a pod dies, services are already built to have an IP that I use to kind of abstract out access to an individual pod. So the Zookeeper pod talks to, like Zookeeper 2's pod talks to Zookeeper 1's service. So when Zookeeper 1 dies and gets moved, the service just redirects and it keeps working. So that worked for me. Yeah. The other trick here, obviously, is if you're doing any sort of dynamic configuration stuff, you have to convince the Zookeeper pods to address or to announce their service DNS and not their pod DNS, because yeah. So the main thing, though, is that this works, but it's tedious to manage, right? Because for each of these pods, which the StatefulSet manages for me, I have to have a service and I have to like label them and stuff. That sucks. So the next thing is that the other cool thing about Kubernetes, or at least the thing I like about it, is what it's moving into is becoming more and more of kind of a generic object API of sorts that happens to have a scheduler. So these pods and these services and stuff are just objects, and I can create them, and I can watch for changes, and I can list them, that kind of stuff. But I can also create my own. And I can also, or like using the Kubernetes API, I can create a custom resource. And I can also have code that talks to the API the same or better than I, the human, can. This next slide is a little busy. We'll get through it. It's okay. But be prepared. So I got a bunch of lines here. So this diamond here in the middle, that's the stateful set, which we had before. So it's managing the 3 pink pods. Those are my zookeepers. I have that in here for comparison. And then this yellowy triangle here is what we call StatefulBuddy. We have a whole suite of these automation tools, which we call Cloud Buddies. StatefulBuddy is one of them, that we wrote for this purpose. So basically here, what we've done is we've created this custom resource. Instead of stateful set, we also have a stateful service. And which StatefulBuddy is just watching. It just lists all of the stateful services and watches for changes, which is super handy. The stateful service points at the stateful set. It just says, I want 1 pod for each of that. And then StatefulBuddy watches stateful sets for changes as well. So anytime you change the number of replicas in Zookeeper, the yellow triangle gets notified, and it goes, oh, great, I'll just go make more pods then. It's given a template, sorry, not pods, services. God. A lot of words. So it has a template for the services that it wants, and it just goes and makes sure that it stamps out 1 service for each pod. And it also, it used to tag the pods to make sure that they were individually discernible. And then it would create the services with those labels. But in newer versions of Kubernetes, we don't even have to do that anymore, because in newer versions of Kubernetes, each pod in a stateful set is natively given a unique identifier, so we can just use that now. So all we have to do is create the services. And again, if a service gets destroyed for some reason, StatefulBuddy will be there to recreate it. It'll say, oh, I'm missing Kafka 1. Great, now I've got it back again, or in this case, Zookeeper. But yeah, so it keeps everything in check. It deletes the ones that we don't need anymore if we scale down, all that sort of stuff. And so we didn't have to, once we spent all the time and effort writing this, we didn't have to do anything anymore, because now it can just watch the API for me and do all those things I was going to have to do by hand, which is great when it works, which this one happens to. There's also, in newer versions, there's a ticket in the Kubernetes issue tracker to just give pods static IPs. There's some people on it. I'm one of them. No one is working on it as far as I know, but like maybe someday that'll just become a feature and then we won't have to do this. But either way, it's still kind of useful to, I mean, if it's not this, it'll be the next thing. And it's kind of useful that Kubernetes allows you to easily hook up to the API and run code against it. Automation is good. Well, except for when it's bad. So the other problem is now all of the things I've talked about so far are great if you want a Kafka cluster that other Kubernetes things uses, right? These names that it provides, Kafka 0.kafka.kafka production.service.cluster.local, is I've had to type that a lot, is great. If you're talking to other things in Kubernetes, this is an internal Kubernetes name. It's not exposed, so if you're running other things on the same cloud provider, sometimes it might be, but usually it's not. If you're still running things out of the data center, maybe, that want to talk to this thing that you're running in the cloud, if you're in like a hybrid approach, then they definitely can't. Or other cloud providers, if you're multi-cloud provider. None of them can talk to your Kafka brokers because all of the ways of addressing in are meant to be a big load balancer that just says, give me 1 of 100 of these. So what you really want is some sort of service that points directly at an individual pod that is accessible from the outside that you can use to address an individual pod no matter what its IP is, which I happen to have already built on the last slide. So basically, we just have StatefulBuddy again. This time the arrows, I could not get them to line up, and it's actually really bothering me. So hopefully no one in here is sensitive to that kind of thing. But anyway, so basically, StatefulBuddy can come back, and it can create a service for each Kafka pod this time. But the Kafka pods are, the services that it creates, rather than being internal, are external. So I end up with this external service, internet traffic can reach them, but there's 1 per Kafka pod. So things that are outside can still talk to like kafka1.whatever.com and receive the broker they were expecting to, no matter where it's been scheduled in the system. And again, StatefulBuddy does all the like making sure that everything's up to date and scaling and stuff. Basically, it's the same as before. Oh yeah. So now there's a little bit more of a problem. Well, it's not necessarily a problem. It's a difference. If you're used to running things in the cloud, then this is actually great. You don't have to listen to this slide at all. But if you're used to running things in the data center, in order to have your pod receive the same storage, no matter which node it's scheduled on, you have to be able to mount this storage onto a bunch of different machines. Nodes, we'll call them. Which, unless you have a person who's getting pinged by machines and running around unplugging things from data centers, kind of means that your storage has to be network available, right? Because different machines need to be able to talk to it at any time. This can be fine, but it can be different if you're used to running things in a data center or if you're used to using local disks where the disks are right there. It's not necessarily bad, but it's definitely a little different. The latency can sometimes be higher or more variable, right? Because it's using network bandwidth now and not I/O bandwidth. I mean, there's also I/O in there, so you can maybe have limits that you aren't used to on a hard drive that's plugged directly into your machine. In some cloud carriers, it might count against your network bandwidth. Maybe there's a cost, or maybe it's just it's using up a resource, right? So this is fine, but this is kind of a source where right now we're still tweaking, right? Sometimes things don't work quite the way we're used to, and all of a sudden it'll be great, and then something will get really like high latency, and then it'll go back down, and we're not really sure why, because we didn't do anything. So maybe it's this. So we're still working on this one, but you should be aware going in that maybe this is a thing. There's an alpha in a new version of Kubernetes that I haven't used yet that has a local volume type, which is meant to abstract around this concept and say, okay, I don't want a network attached device. Give me essentially a folder on the machine I get scheduled onto, and I can put all my data in that. And I think it has the advantage where if there is a if there is a Kafka 0 somewhere that has, a machine somewhere has Kafka 0's data, schedule us onto that. And if there isn't, schedule us somewhere and then always back onto that machine again in the future. I don't know if it actually works that way. That's the way I hope it works. In which case it would be this nice middle ground where, because Kafka has redundancy, right? We can lose a broker and just rebuild. We just don't want to have to do it every time we change a configuration variable. Yeah, so that. So maybe that'll be a middle ground someday, or it won't. And this just is a thing you have to live with. Yep. Okay, new problem. So you've got a big cluster of nodes, and you've got a whole bunch of them, and you've got work on them. Some of them is Kafka work, some of them might be web servers, some of them might be job workers or data processing things. And suddenly, you have to schedule a new Kafka broker. Maybe you've scaled up, and you have a new broker. Maybe a node has died, and you just want to move to another node. It could be a restart because you changed some configuration, whatever. This is great, but the Kafka brokers, let's say they're big, right? Let's say your machines have 130 gigabytes of RAM, and your Kafka broker has 99 or something. You can run into this situation where I've got this big pod that doesn't fit on any of the nodes. If I add up the total that I've used and the total that's available, I have more than enough space, but no individual node has enough space for this thing that I'm trying to schedule right now. And currently in Kubernetes, what it will do is it will say no. It'll just say, I cannot find any nodes that satisfy these constraints. I'm really sorry about that. And then if something dies, then it'll put it in there. And if a new node suddenly appears, it'll put it on that. But in an automated sense, you can't just magically have more nodes, which can be a problem. So there's not a great way to fix this. So to fix this, what you basically have to do is have a separate set of nodes, or you can. So now I've got these yellow nodes and these purple nodes. And the yellow nodes, the Kubernetes feature is called, they are tainted, which basically says you cannot use these nodes unless you specifically declare I can use Kafka nodes, which only the Kafka brokers do. So now I've got this pool of nodes that's separate from the other nodes that only Kafka can run on, so I can know that there will be space when I need it, right? I have 13 machines, I have 10 brokers, or whatever the numbers are, so there will be room if a node suddenly dies, I have room to schedule it, because I don't have all these web pods gumming up my machines. This is kind of a drag because it puts a little bit more operational work back on the human, right? One of the purpose of Kubernetes was so that I could just have a big bag of machines and just throw work at it. And now I have to have two bags, a little bag for Kafka and then like another bag for other stuff. But it's better than not having brokers come up. And there are some advantages, like I could maybe upgrade my pool differently than everyone else upgrades theirs, so that could be okay, I guess. But it'd be great if we didn't have to do that. So there's an alpha feature in newer versions of Kubernetes that I have not used yet that's called pod priority and preemption. And basically it allows us to declare all of these pods are 0, right? They're all normal, and Kafka's important. And then basically the scheduler at that point can say, oh, I've got an important node, an important pod that I need to schedule, so there's no room to schedule it right now. So if I just go kill these things though, and then I can put it there, and then those less important things, they'll get rescheduled somewhere else probably. In which case I could have one big bag of things again. I don't know if the feature will actually be great because I haven't used it, but I'm excited about it anyway. One last thing, running a little low on time, but one last thing. I think this is the last thing, is just something to be aware of because it tripped me up a little bit when I was looking at the balance sheet. So most cloud providers have this concept of a failure zone or an availability zone or something. So if you're running in a cloud in like the EU West 1 region or something, that's probably a thing. Then they might, in order to survive a data center loss, they usually have multiple redundant data centers in the same region. So these are all EU West 1, but this is West 1A and West 1B and C and D or whatever. And these things are meant to have redundant power supplies, and they're meant to have redundant networks and stuff so that a failure in A doesn't cause all of the things in B to die as well, which is great. So this kind of lines up with Kafka's rack awareness feature. So which makes sure that the data is spread out so you can survive a rack failure, which is a smaller version of the same problem. So basically, we have a startup script that basically just says, when I start up, I figure out what node I am on, I figure out what zone that node is in, and then I use that string in my rack awareness configuration. Which means that later when I'm distributing partitions, I make sure that replicas are always on different racks, which are always in different zones. And so I end up with a look that kind of goes like this, where the data comes into one of the brokers, and then like a copy of it goes out to the different zones, never the same zone. This makes perfect sense. But something that you should know is that a lot of cloud providers charge differently for traffic between zones compared to traffic within a zone. So if I were to replicate in this top left quadrant here, the traffic might be free. I would get charged when a data ingress comes in, and then never again. But most providers will charge something when it goes between zones. So in this case, I would get charged for this individual message 4 times. Once when it comes in, and then once when it crosses each of the other boundaries. This, again, it's fine. It's the way that you should do things, right? Because having all of your data, if you were to somehow configure it so that all of your data just replicated within a zone, it would be cheaper. But then if the zone died, you have partitions that go offline, which is not so great. But you should know that when you're expecting a certain value to come out at the end of the month because of the number of messages you had produced, and it's more than that, you don't be too surprised because this is a thing that might be in there. There might be hidden costs a little bit. It's just something to watch out for. Like I said, Kubernetes is popular right now, and its popularity is only increasing, it seems. And so the community is actually pretty active. There's all sorts of people from different companies and hobbyists and stuff that are producing features. There's a lot of tickets. Every time a new release of Kubernetes comes out, which is every couple of months it seems like, some new feature becomes available. So for example, up until like 2 versions ago, which is like 6 months, the StatefulSets didn't have rolling restarts, so you had to specifically orchestrate a rolling restart yourself, but now they do. In new versions, like I said, this pod priority is going to be coming up. So there's a couple of things that are kind of on my radar. Static IPs coming up might be really helpful, so you don't have to have a StatefulBuddy of your own. Local volumes might be really cool, but they might be terrible. Pod priority sounds like it'll be pretty great. Another one that didn't really fit into any of the slides is like volume resizing, for example. So like right now, if you have 6 terabytes per broker and you want to have 10, it's a big manual dance. But in the future, you just be able to change 6 to 10 and hit go, and then it'll just kind of roll through and make all your disks bigger like magic. Hopefully. I haven't tried that one yet either. Last slide. Okay, so this is kind of the part where everyone, there's a bunch of people here, and this is the part where you're all disappointed. So the retrospective. I don't, like, if we had to do this all again, would we? And the problem is I don't know. It's definitely different than running things in the data center, right? Even if you're using something like Chef or Puppet or Ansible or NixOS. Is anyone using NixOS? NixOS is cool. Even with those systems that manage machines, it's definitely different. And so you have to be kind of, on the one hand, you have to be careful of the thing that's new and shiny, but also like it does have some cool features, right? Like the fact that I can just type a thing on the command line and just blow away 4 machines, and then they just kind of like come up from other parts of the earth without me having to do anything is actually pretty great. The whole reason we kind of started this experiment is because a lot of our other parts of the company were also trying out Kubernetes, and it was useful to be able to be on the kind of the same page as them. Some of the things that we developed together with other teams because we all needed to be able to schedule things in this way. So that was kind of handy to have one unifying automation API that was really great. But it's also sometimes harder to figure out what's going on, right? You can't SSH into the one machine that's always Kafka 4 and look at dmessage and see what it's doing because it's this cloud of machines that run all sorts of stuff in Docker containers, and like sometimes it gets a little tricky. It can sometimes be a little bit less predictable, which isn't usually what you want in your message bus infrastructure. But Kafka's pretty resilient to that kind of thing too, because it inherently didn't trust the machines to begin with. One of the things with all of these is like it can sometimes be a little bit easier to accidentally propagate failure. Kubernetes' API is actually really nice, like its command line interface. The way how you can just say scale 4, enter, and then it just goes up to 4 is really great. And so you might not want to build a lot of tooling around it because it provides a lot of tooling, which is great. But it's also really easy to mean to type 40 and miss that 0, and then you hit enter, and like all of a sudden 36 of your brokers shut down. It's easier to spin them back up because you just put the 0 back on there. But like it can be sometimes too easy to make sweeping changes. So again, be careful. It's not always as perfect as it seems. And it also, like a lot of tech, it took a relatively short time to get everything running, right? You can basically go online right now, download a Kafka and Zookeeper.yaml, and push it up to a Kubernetes broker and have something running, or a Kubernetes cluster, and have something up and running in 10 minutes. But then it took a lot longer to iron out the kinks, and even to find what the kinks were was kind of surprisingly complicated sometimes. Something would just be weird for a while. But on the other hand, it's also kind of nice because the week before I came here, I spun up a new cluster, and it was basically like, click the button, send, and then it happened, which was kind of nice actually, once all the automation was there. So I don't know, it's very useful. I think it's cool. I like it as a human, but it's not perfect, and you should all decide for yourselves, despite the fact that this is a talk about that. And I think I burned through all my question time.
We have 5 minutes.
5 minutes? Yeah. A bounty.
So I have 2 microphones, so if anyone wants to ask a question.
Oh wait, before the questions, I'm going to be available if you want to ask one-on-one questions, you can just come find me. That'll be great. So kind of more general questions are probably more useful given that we have very little time.
Hi.
Hi.
Did you experiment with Kafka Helm?
No. So Helm is a whole side of the things that I have not looked at all. Part of that is because it was like, oh, I don't need Helm. Look, I've got these YAML files right here. They'll work great. And also part of it is just that for whatever reason, none of the rest of our organization is looking at Helm either. I'm not saying it's a bad thing. I think we just haven't looked. That would probably be, if it's great, that would be great. I think one of the other problems is we're a little bit, I don't want to say distrustful, but suspicious. It can sometimes make things harder to either audit or even to know what it's doing, because like you click go and it works, and then if anything's broken, it just is. And it's like, okay, I'll go like dig through this big thing, and I'll like make a fork, and I'll merge that over here or something. It's probably not too bad. I'm overselling it. Yeah, so no, the answer is no. Maybe someday.
Hi.
Hi.
Just to get a sense of the operational effort involved, how large is the team? How long did it take to set this up? And what's the day-to-day like?
So the team that touches Kafka on the day-to-day is about 3, and it was basically me and then a bunch of like occasional help doing the stuff. I mean, no, that's not fair. That's not fair. But like, let's say 3. And as for how long it took, it's actually kind of I don't know how to measure it. The first deployment took a week or 2, maybe. And then since then, it's basically just been small bits of toil along the way where it's like, oh crap, we have to do this, or like, oh, this is kind of weird. And so like we've been the first deployment probably finished over a year ago, and we've been running it in production, or like part of production, because we have things all over the place. But in part of production for like maybe also about a year. So let's say like 4 months before we moved it into some part of production. But there have been things along the way. So we haven't been doing nothing on it over the past year, but we also haven't been working on it constantly over the past year. What was the other part? Day-to-day. Again, the day-to-day is mostly fine. Mostly it just does its thing. And like a broker might go down every once in a while, an alarm goes off, and we're like, oh no, it's back. Which is exactly the hope. Every once in a while, something goes weird, and almost all of those so far have not been Kubernetes' fault. They've been like the cloud providers, like oops, we had a network outage, or like, oh no, all of these things went away. So like the last kind of big outages I can think of that were actually related to Kafka and Kubernetes in particular, I can't. But I'm sure there was one, and it was important. But yeah.
One more question over here.
Okay. Sorry, was that?
Yeah, there's I think in Java 8 update 131 they added a new switch which was use C group memory limit for heap.
Yeah, that's the one.
Which will allocate, say, 70% of the memory from the container, not from the node. I just wonder whether you tried that with Kafka.
No. No. I don't. We're not running. What did you say? 131?
I think it's 131.
That actually sounds like quite a while ago. Oh well. No. In this case, we kind of we really wanted to specify a particular heap size anyway, and I was just cutting corners. When it was like, okay, I'll just click go and it'll just do the thing, and it did not. But yeah, so yes, like I said, with modern versions of the JVM, you can have an option and it will do that for you. But in this case, the right thing to do was to specify a particular heap anyway. But the feature is there if that was a thing that turned you off from the whole thing.
Any more questions? All right. Well, thank you, everyone. Put your hands together, and don't forget to fill out your survey.